Welcome to this demonstration of Autodesk Nastran in Inventor. During this video, we're going to find out if the material we're using for the crane does not yield and ensure the model will not buckle under a 20,000 Newton load as a factor of safety. Buckling may occur in areas of the design where there is a loss in stiffness due to compression. It is often dangerously overlooked and can be analyzed right here inside Inventor. We're only going to run the solver on the boom by itself, so we'll hide some of the other components. Autodesk Nastran is fully integrated in Autodesk Inventor. There is a Nastran tab in the ribbon, as well as the FEA browser for easily setting up the linear static and buckling studies we're going to solve. The material can be selected from the Autodesk Material Library or imported directly from the CAD model. Here we can select the parts we're going to analyze from this assembly and confirm the material, as well as the element type to use, such as solids, shells, and beams. Next, we'll specify a bonded or welded contact between all the components. Then we can mesh or divide the part into several pieces to be analyzed. Now we'll apply some of the boundary conditions that simulate a real-world scenario. We're going to start with a fixed constraint at one end of the crane. Then we have two holes used for the actuator that is lifting the boom up and down. In order to simulate a bearing, we'll add rigid connectors from the nodes on the model to the center of the hole. All of the boundary conditions contain the option to keep the dialog open for adding additional items using the same information. The 2 points can now be used to apply a constraint that can rotate but does not translate. Notice there are options to allow translation or rotation in any of the 6 degrees of freedom. Finally, there is the force for lifting an object. The load will be applied in the direction of gravity, which in this case is the z direction. The x, y, and z directions can refer to the coordinate system in the main assembly or any of the parts included in the analysis. We've completed the setup for the linear static study. Let's go ahead and run the solver and view the results. There are many plots available for viewing the stress on the model. We'll start with the von Mises plot to find areas of high stress concentrations. Before displaying the plot in the graphics view, we can already see the highest value in the legend is already more than 300 megapascals. As we pan over the model, we're observing most of our concern is on both ends of the actuator plate. There are also principal stress plots for focusing on tension or compression on the model. Let's have a look at compression. Underneath the steel tubing, we can see we have almost 100 megapascals of compressive stress. The material won't yield here, but it might cause a buckling failure. Once again, the buckling study is available in Autodesk Nastran and can be set up and run right here in Inventor. By changing the study, we're simply adding a subcase so we can view the stress and buckling results in the same analysis. The boundary conditions for the linear static study can simply be dragged into the new subcase for buckling. This time we're interested in the highest load we can apply before the structure fails. So we'll change the load value to 1 Newton and the solver will produce the buckling load factor. Let's run the study and view the buckling results. The solver is sped up during this video, which takes about 4 minutes to solve for this assembly. Remember, the values for each mode will provide a buckling load factor. The first one we're observing is showing a load of just over 2,600 newtons. We may want to make modifications to the model dimensions to avoid catastrophic failure for larger loading conditions. We'll make the changes right here in Autodesk Inventor. The new design will be reanalyzed in Autodesk Nastran without the need to leave the CAD system. The size of the steel tube will be made 20 millimeters wider, and the gauge thickness will be 4 millimeters instead of 2. We will also change the thickness of the actuator plate since it adds stiffness to the boom. Let's update the mesh and run the solver one last time, and find out if the changes to the geometry had a positive impact on the buckling results, as well as the high stress concentrations. We are now seeing load factors of over 22,000 newtons, meeting our engineering goal mentioned at the beginning of the video. It took minutes for us to view the results from the original design and make the necessary changes, as opposed to days to create a costly physical prototype. We can also see that the stress results have decreased to a factor of safety of 2. Remember, this is only a 1 Newton load. The highest stress can be multiplied by 1500 to compare to the previous results. This workflow not only saves time and money during the design process, it also ensures a safer product and fewer warranty claims from the customer. Autodesk Nastran in Inventor helps to make better products using digital prototyping.